Cole, can you read to me the title? Lesson 4.
Conservation of momentum.
Conservation, or when something is conserved, has a special meaning in science. You may have seen it in chemistry when you learned about conservation of mass. Later on, we'll be talking about the law of conservation of momentum. If something is conserved, what that means is whatever you start with is whatever you end with. It doesn't vanish. And it turns out momentum is conserved. But we're going to start off with a little thought puzzle. It says this. Let's suppose we have a big moving van and a little tiny car, and they're heading towards each other. Which one is going to experience the larger force? A, the truck, B, the car, or C, both the same? You know what? We get to vote. How high we hold our hand up is how sure we are of the answer. So in this collision, who says the truck experiences the bigger force, Mr. Dewitt? The truck. The truck. Dylan says the truck. We got one. The truck is going to experience a much bigger force. Who says, Mr. Dewitt, the car, the car, the car? 1, 2, 3, 4, 5, 6, 7, 8, 9. Who says both the same? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ooh, we have almost an even split. Convince me. Christian, did you go back to Newton's laws? What did you just say? So what's the correct answer? And you can either write forces come in pairs, or you can write Newton's third, because that's what it was. Both vehicles are going to experience the same force. Now, I already see about, 9 of you, those of you that picked car, and you're frowning at me because you're imagining the collision. I didn't say which vehicle experiences the most damage. I said which vehicle experiences the most force. The forces are identical. So then, the logical question is, why is it that the car and driver are almost always worse off than the van after the collision? Emma, F equals what? So is the force the same? Because I know you shot your hand up for answer C, the force is the same. So you were correct. Are the forces the same? And F equals what? So, same force, but for the truck, we have a really big mass, which means only a tiny acceleration. For the car, we have a smaller mass. That means there's a big acceleration. And really what does damage in an accident is not the force, it's the acceleration. The acceleration. Okay. But are the forces the same, Emma? Say yes. That's going to have a profound impact. I have to give you a bit of a definition here. A closed system, this is a physics term. This is one that's cut off from the outside world. You'll see me refer to this, or I'll say, assume we have a closed system. What we mean is there's no outside external forces. Whatever you're looking at, everything has been given a push, and then we've let go of it. No one is continuously still pushing on an object while we're looking at that. Some systems, some examples of closed systems include frictionless systems like ice, frictionless surfaces like ice. So on ice, you'll keep going in a straight line at a steady speed because there's no forces acting on you. It's a closed system. Deep intergalactic space. On ice in real life, Brian, there's a tiny bit of friction, so ice is only a theoretical closed system. Perfect ice would be a closed system. Actually, perfect ice in a vacuum would be a closed system. You know what? That's how outer space behaves. In outer space, if you do give something a push, as long as there's no planets nearby, it's going to keep going in a straight line at steady speed. Systems floating on the water. Water actually has very little friction unless you're plowing into the water. But if you're floating on the top, you'll skim along quite a way. And objects that roll. All right. For collisions in a closed system, the contact forces are governed by Newton's third law. Christian, what is Newton's third law? And which means that they are equal and opposite. Now, if the forces are the same, but opposite, so call one negative, call one positive. But if the forces are the same, and I think it's reasonable to assume that the time of collision is the same for both the truck and the car, because it's the same collision for both of them. I don't see how you would have the time of collision last longer for the car than for the truck. They're in the same collision. What that means is, so the forces are the same, Christian says. The time of collision is the same, which means the impulses are the same but opposite. Because force times time is impulse. What's another word for impulse? The change in momentum is the same. What does that mean? If the car loses 20 units of momentum, what happens to the truck? I'll give you a hint. Your answer will include the phrase 20 units of momentum. Gains. Momentum is not lost, it is conserved. And the reason it's not lost, the reason it's conserved is because forces come in, and the time of collision has got to be the same for both of them. So they both have identical but opposite impulses. If the truck loses 50 kilogram meters per second of momentum, the car gained 50 kilogram meters per second of momentum. And that's true for any collision. In a collision, momentum is conserved. So, since momentum change is equal and opposite, the momentum is not gained or lost. It is simply transferred, and the fancy word we're going to use is conserved. And that's going to allow us to analyze collisions. Turn the page. So here's our car and truck again. Suppose they end up at rest after the collision. How can we say that we haven't lost momentum? So here's our before, here is our after. What's the final momentum of the truck? What's the final velocity of the truck if it ended up at rest? 0. So what's the final momentum if momentum is mass times velocity? 0. What's the final momentum of the car if it ends up at rest? 0. So what's the final momentum, what's the overall, did I say final momentum? What's the final velocity of the car? 0. Final momentum, 0. What's the overall final velocity? Momentum final equals 0. What that means, Matteo, is that the initial momentum must be 0. Matteo, momentum is what times what? No, that's change in moment, just straight momentum. From your sheet, P equals mass times velocity, mv. Momentum is what times what? mv. Does this have a v? Does this have a v? How the heck can that be 0? Well, let's break it down. So we have the momentum, let's change colors, Mr. Duke, of the truck and the momentum of the car. What did you say momentum was equal to? Not impulse, but just momentum? Yep. So this is going to be mass, Emma, can I use T for truck? Initial velocity of the truck, that's I with a T, they overlap. Let me try that again. V initial truck, and M car, V initial car. Matteo, what is the mass of the truck? What is the velocity of the truck? What's the mass of the car? What's the velocity of the car? Not 24. Because this is my rant earlier when I said to Emma, we have to pay attention to direction changes. And we ought, absolutely, in most collisions, you will have direction changes. We have to call one positive and one negative. And really, Emily, you have to do this on your calculator. Isn't it 24,000? Take away 24,000. Isn't that what you get? So what was my initial momentum? What was my final momentum? Momentum was conserved. My initial momentum was 0. My final momentum was 0. Momentum was conserved. We're going to bring the fan out, or are you going to make it? Kilogram meters per second and 0 kilogram meters per second. That's how we were able to say that no momentum was gained or lost. There was no momentum to begin with in that overall system. Each of them had identical momentums, and they were in opposite direction. Now, I cooked these numbers, Matteo, carefully to give us that exact 0. But the law of conservation momentum does hold. What does the law of conservation momentum say? It says this: in any collision or explosion in a closed system, momentum is conserved. And this means that momentum is not created, it is not destroyed, but it's transferred from one object to another. You can write this several ways. Tristan, one way is to write it out in English. The total initial momentum of a system equals the total final momentum of a system. Do you think I'm going to write it out in English every time? No. You can write it out mathematically. P of object 1 initial plus P of object 2 initial equals P of object 1 final plus P of object 2 final. That only works if there's 2 objects. If there's 3 objects, you'd have to have momentum of object 1 plus momentum of object 2 plus momentum of object 3 equals momentum of object 1 final plus momentum of object... Okay. Matteo, momentum is what times what? So this one down here, I just replaced every P with an MV. I have to be honest, the one I go to the most is this one. This is my preferred. And why? It's shorter and it's nerdier. Now, what the heck does that mean? Some of you in Math 12, if you're in grade 12, may have come across this. You may come across this in Pre-Calc 11. There's that funky, that thing. It's a Greek letter. Does anybody know what Greek letter that is? For a candy? Wow, no nerds here. This is the Greek letter sigma. It is where our S comes from. Really? Because if you write it fast, you get that. And if you write it fast, you get that. And if you write it fast, you get that. If you write it fast, and you slowly, over time, morph it into an S. But what it means is the total, or the sum of. And because, Matteo, you've had me enough to know that I tend to abbreviate, I go with that one. Is there a collision? Then the total momentum we started with equals the total momentum that we finished with. So it really is this sentence here as a symbol. Whichever one you want to use, I'm going to almost always start with this one here. Here's the key. We use conservation momentum. How am I going to abbreviate conservation momentum? C of M. We use the law of conservation of momentum whenever there is a collision or an explosion. I'm going to say that a little bit differently, Rihanna. Listen close, because I'm going to come to you. We use it whenever there is a collision or an explosion. We use it whenever there is a Jean. This brings me to a lovely example of conservation and momentum. Some examples. Okay. Example 5 says, find the missing velocity, magnitude, and direction. I told you before the lesson, Misha, that this is going to allow us to do crime scene investigation, car crash investigation, the physics of car crashes. So I guess we have car A going forwards and car B is in reverse. Okay? Is there a collision? This is a job for conservation of momentum. Is there a collision? This is a job for conservation of momentum. So in the same way as if we were doing forces, that was a job for a free body diagram. If you want my trigger here, is there a collision, Emma? Conservation of momentum. Now what does conservation of momentum say? It says this. The sum. Let's change colors, Mr. Dewick. By the way, look up. A proper typewritten sigma looks like that. but we get lazy and we do it like that. The sum, the total of all the momentum beforehand equals the sum, the total of all the momentum afterwards. That right there is the law of conservation of momentum. Okay. Sierra, looking at the picture before the collision, what's moving? Car A, car B, both or neither? Yep. Before the collision, are they stuck together or are they separate? They're separate. So here's what I'm going to write. The momentum of car A initial and the momentum of car B initial. That's how much momentum we're starting with. Wham! They collide. After the collision, Sierra, what's moving? Car A, car B, both or neither? Well, definitely car B. And since they want me to find car A's velocity, I think both. Stuck together or separate? Car A finals momentum and car B finals momentum. This is, again, one of those times when you're going to have to derive an equation on your own, much like you did with forces. But, Rihanna, during collisions, they're all going to start out like this. And then you're going to do exactly like I did with Sierra. Before the collision, what's moving? A, B, both or neither, stuck together or separate. After the collision, what's moving? A, B, both or neither, stuck together or separate. Mateo, momentum is what times what? So I'm going to argue that the momentum of A initial is the mass of A, velocity of A initial, plus the mass of B, velocity of B initial. Wham! They collide. Mass of A, velocity of A final, mass of B, velocity of B final. This is the law, Jacqueline, of conservation of momentum. The amount of momentum you started with equals the amount of momentum you ended with. Sarah, what are we trying to find? Velocity of car, final or initial? Okay, folks, how am I going to get this by itself? Well, there's a plus MBVB. How will I move the plus MBVB? Subtract? Okay, so my next line I'm going to go like this. I'm going to drop the mass A, velocity A initial down like a domino. And I'm going to drop the mass B, velocity B initial down like a domino. And you're telling me, Sierra, I'm going to subtract the B over? Yes? I'm going to write the next step. I'd like you not to write this. I'd like you just to imagine this. So Sierra, and then left over I have M, A, VA final. This is what I'm trying to find. How would I get the VA final by itself? Divide by what? This is what I'd love you to write. This is, if you want to, you can go straight to saying this is VA final, and you can say I would divide that whole thing by the mass of A. This is absolutely not on your formula sheet, because for me to try and come up with every possible version of car accidents, I'm just not going to try. What is on your formula sheet? That bad boy. When do you use that bad boy? When there's a collision or an explosion. We'll talk about both. We're spending a couple of days on this. Now we've got it to the plug and chug stage. So here we go. To find the velocity, the final velocity of car A, we have MA. Sierra, what was the mass of car A from the picture? What was the velocity of car A from the picture? Plus, what was the mass of car B? Be very careful. What was the initial velocity of car B? Yes. And you have just decided for all of us that to the right will be positive and to the left will be... Okay, you could have done it the other way around. There's no hard, fast rule here, but there is definitely a change in direction. What would be wrong is to call them both positive. Then I have a minus sign. I have a 2,000. After the collision, what's car B traveling at? Positive or negative? Positive, okay. Divided by 1,000. Sierra, is this a fraction? Say yes. Is there more than one thing on the top? brackets around the top. Is there more than one thing on the bottom? Me. Times 10 plus 2,000, whoop, not 20,000, 2,000 times negative 2. Take away 2,000 times 4, close off the top, divided by 1,000. You'll get negative 2. What's the negative telling me as a direction? Left. Okay, so if you wrote this, I'm okay with that. Or if you wrote 2 meters per second left or west, I'm okay with that. I would just be grumpy if you wrote negative 2 left, because to me negative left actually means right, I would argue. Use one or the other. That's the law of conservation of momentum. Now, we used this. We knew both of the initial velocities, and we found one of the finals. If you knew both of the finals, could you find the initial velocities? That's what the RCMP are doing when looking at accidents. B. Tristan, my friend, is there a collision in B? This is a job for conservation of momentum. The sum of all the momentum that we started with has to equal the sum of all the momentum that we ended with. The total momentum initial equals the total momentum final. Tristan, before the collision, what's moving? Car A, car B, both or neither? And what are they asking me to find here? Let's assume it's moving, because if the answer was 0, that'd be pretty boring. So, car A, car B, both or neither? What's moving? Car A, car B, both or both? Look, stop. Are they stuck together or separate? Well, if they're coming towards each other, they must have been separate, because this is about to be sort of I'll call it a head-on, but they're just not facing each other. Okay, so I'm going to argue, Tristan, that we have this. The momentum of car A initial and the momentum of car B initial. This is what's going on before the collision. Is that all right? Good. Ah, they collide. Every collision, Mr. Duick? Maybe. Nick, after the collision, what's moving? Car A, car B? Both or neither? How do you know? Two different velocities. Yeah, okay. Stuck together or separate? Since they're traveling in opposite directions, separate. So we're going to have the momentum of car A final and the momentum of car B final. Tristan, my friend, momentum is what times what? On your green sheet, P equals? Can you show them where it is, Nick? Yep. So I'm going to argue that the momentum of A is going to be the mass of which car, Nick? A. And velocity A initial. And the mass of B is going to be the mass of which car, Tristan? And velocity B initial. Wham! They collide. Afterwards, we're going to have mass A, velocity A final. Mass B, velocity B final. You okay with that, kiddo? What did you say they're asking me to find, Tristan? Initial or final? Yeah, final, that's 2, right? Initial? Okay, so we're trying to get this by itself. First thing I'm going to do is move this over. How am I going to move that over? How am I going to move a plus MB VB initial over? Good. So, you ready, Nick? You ready, Tristan? Let's see if we can do this in one step less than we did it on the previous question. What do you say we're going to do? Subtract it? So what's going to drop down like a domino? The mass of A, velocity of A final, plus the mass of B, velocity of B final. The right-hand side drops down. What did you say I'm going to do with this thing? So it's going to be a minus mass B, velocity B initial. You okay with that? Can you just imagine that this is right there, how they get the V by itself? What's the M doing? What's the M doing to the V? How I'll move the M over? Which M? M of? Mass of? Yep. So this is what we'll write down then. VA initial equals MA. And now we've got it plug and chug. Complicated plug and chug, I'll grant you, Tristan, but there it is. And again, don't try and memorize this equation. Don't even try and memorize this equation. If there's a collision, all of the momentum you start with has to equal all the momentum you finish with, and then adjust it to your specific situation. What's moving before? Stuck together or separate? What's moving after? Stuck together or separate? We'll do some where we're stuck together in things as well. Yeah, Tristan, reach for the calculator. I got to fill these in. I've scrolled down, Nick. What was the mass of car A? 1,000? What was the final velocity of car A? 2? Okay. What has Nick just decided? He has just decided that left is positive. And you can do that the whole way if you want to, or would you prefer to let left be negative? Okay, you sure? Okay, so, by the way, you know what I would have done right away? I would have probably gone negative, positive, negative. The 3 is negative, yes. And I would make a little note, I'm expecting a positive answer here. If I get a negative answer, I probably botched something up. So you're telling me negative 2 plus mass of B, final velocity of B, minus 2,000, initial velocity of B. Is that right? Didn't we just finish writing a negative up there, dude? Okay, and I'm going to say for you, that's a sloppy mistake. After that song and dance, we can't get that wonky, right? Divided by mass of A, which was 1,000. Hopefully you do get a positive answer, because I was picking these numbers from the internet. Velocity of A, initial. What do you get? 12? Positive or negative? So we can say positive 12 meters per second or 12 meters per second. Direction, Nick, which way did you let be positive after I talked you into it? Right or east, or what? If the question had given you a compass rose, I would use northeast, southwest. Otherwise, I tend to go right and left. By the way, if you look at this collision, here's really what we're saying. The first car B is moving backwards. Car A is moving forwards. Wham, they collide and they bounce apart. Do objects always bounce apart? No, sometimes they stick together. Question C. Question C. Colon, question C. Is there a collision?
Yes.
This is a job for conservation of momentum. The sum of all the momentum beforehand equals the sum of all the momentum after. Cole, before the collision, what's moving? Car A, car B, both or neither?
Probably both.
Stuck together or separate? Before the collision, since they got to be separate because they're coming this way. Yes?
Yeah.
So I'm going to have this. Momentum of A initial, sorry, momentum. Yeah, momentum of car A initial plus momentum of car B initial. Are you ready? Wham! They collide. Really, Emma? After the collision, Cole, what's moving? Car A, car B, both or neither?
Both.
Stuck together or separate?
Stuck together.
So let's write this. Momentum of both. Because they're stuck together. Fine. Okay. Cole, momentum is what times what?
Mass times velocity.
So it's going to be mass of car A, velocity of car A initial, plus mass of car B, velocity of car B initial. What did I do both? Oh! How about this? Bracket mass A plus mass B V final. I think that would be the momentum of both stuck together. They must be going the same velocity because they're stuck together. Cool, what am I trying to find?
VA.
Oh, I'm trying to get this bad boy by itself. How? What do I do with this? Okay. So what's going to drop down like a domino? The bracket here, we're going to have mass A plus mass B V final. You're telling me I'm going to subtract mass B VB initial? I don't quite have the A by itself. Sorry, the VA by itself. How would I get the VA initial by itself? Ooh, look at you. You're telling me that's VA initial? Now, by the way, you'll notice I'm writing a vector sign above all my V's, and that's Nick because I want to pay attention and remind myself to pay attention to changes in direction. How come I don't put a vector sign above the M's? Scalar. Who cares? They don't have a direction at all. But I'll just, that little bit, I think Nick really helps me to prevent me from making silly mistakes like, oh, I forgot the direction. All right. Cole, my friend.
Yeah.
What's mass A?
2,000.
What's mass B?
4,000.
So this is going to be 6,000. V final
5.
minus mass B 4,000.
Yeah.
Velocity of B initial
-3.
-3
Yeah.
divided by 2,000.
Yeah.
What do you get? How fast was car A coming in? Are you starting to see where you could use this, Oliver, in crime scene investigation and RCMP crash investigation? Yeah. We have the incoming velocity of a vehicle. You get 30,000 plus 12,000. You get 42. 21,000? No. 21? Positive 21? So you can either write positive 21, or if you wanted to give it a direction, what would you say? Turn the page. Is this the last one? Yes, it is. I'm going to perhaps let you know how old I am. I don't know if you call it what I recall calling it. When I was a child, if you got going fairly fast on your bike and then you jumped off and you let your bike keep going in a straight line, we called that ghost riding. Because we said there was a ghost riding do they? Nothing. Okay. Nobody's nodding. That's clearly something from my... Do we still call it underducks on a swing when you... Okay, so that term hasn't changed? You got that one? Okay. Well, we used to also call it ghost riding when I was a kid. You would hop off and the bike would keep going. Usually did it in the field so that when your bike did crash, you didn't wreck it on the pavement or anything like that. So, that's what we're doing here. Is this a collision? Well, actually, this is two joined objects, the bike and rider, coming apart. I would argue that's an explosion, a slow explosion, but I would argue an explosion is the reverse of a collision. In a collision, objects come together. In an explosion, objects come apart. And my point is, this is a jeune. This is a job for conservation of momentum. So we're going to go like this. The total momentum initial has to equal the total momentum final. Chloe, before the explosion, what's moving? I guess we have R, the rider, the bike, both or neither. Stuck together or separate? Okay, so I think we can now say we're starting out with the momentum of both of them initial. Wow! That's what it says. After, I think both and separate. So momentum of rider final, momentum of bike final. Now, you may find as you get good at these, Jacqueline, that you can combine some of these steps or take some shortcuts or, yeah, you know what, I can do that line in my head and go straight to the next line. And I'm okay with that in your homework. In our notes here, I'm showing you a very meticulous way to get there. Chloe, before, momentum is what times what? Okay, you know what, let's see if we can be bold and go straight from this line to the numbers without writing mass, velocity, mass, velocity, mass, velocity. So momentum of both is going to be mass of both. Yeah. Velocity initial of both. Whoa! Mass of rider. Velocity initial of rider. Pause. How fast was the rider going before? How fast is the rider going now? Did the rider gain momentum or lose momentum? So what must happen to the bike? So I'm already telling you the final velocity of the bike is going to be bigger than 5. You can try this safely with helmets and padding on a field, but if you jump off of a bike, it should speed up if you slow down. Mass of the bike is 20 times VB final. How would I get the VB final? I think I'll minus the 60 and the 20 over and divide by, the 60 and the 2 over and divide by 20. Okay. So it's going to be 80 times 5 minus 60 times 2 divided by 20. I think I can do that in my head. 80 times 5 is 400 minus 120. It's going to be 280 divided by, is it 14? Did the bike magically speed up by gaining energy from nowhere? No, momentum was conserved. Whatever momentum the rider lost, the bike gained. We didn't magically create momentum from nowhere. This is the law of conservation of momentum. We're going to practice this some more with more complicated equations and things, but for now, number 1. Number 2. I think we're going to be doing all of these. Number 3. Ta. Number 4, we have miles to go and Ben traveling. Nothing? Okay. Calvin and Hobbes. We'll do number 5 is cool. Calvin and Hobbes. We'll do number 6 is cool. Now, looking at number 6, I see a head-on collision. I'll probably have to let one would be positive and one would be negative. Number 5, it looks like Hobbes is running in the same direction away from Hobbes. So think about your signs very, very carefully. Okay? This is an introduction to conservation of momentum.